Thank you for coming to the fellowship presentations. The first one we have up is Aneesh.
I guess I'll just introduce myself to start. My name is Aneesh. I'm a PhD student at Cornell. I actually am an engineer, but because I want to advance my PhD research in towards FPGA development or software development on FPGAs, I thought this was a great opportunity, and Isabel was very helpful, supportive, and instrumental in supporting this project, and yeah, and helping me get set up with everything. My project over the summer was to accelerate graph neural networks using FPGAs for online particle track reconstruction. The network I deployed is a simple and shallow interaction network that operates on graphs processed from the TrackML dataset for particle tracking. I won't go into what an interaction network is, as I was focused on more implementing it, but it's just a simple graph neural network. And it basically includes a relational model with 4 linear layers and an object model with 3 linear layers. The relational model is executed twice during a forward pass of the interaction network, and each fully connected or linear layer is that's inside the relational and object models is just a simple multidimensional linear operation, or basically just the output is the input data multiplied by, or input graph multiplied by the layers weights plus some bias term. And on the right side of the slide, I laid out a simple view of a forward pass through the interaction network. Basically, every operation can be accelerated on the FPGA, and it boils down to transposing and concatenating matrices, running them through activation functions, and multiplying them with other matrices. And during development, I started by deploying the network on an FPGA on a small amount of data and optimized the implementation for runtime and throughput efficiencies. And then I scaled up the data size. So FPGAs are semiconductor integrated circuits that can be configured repeatedly to perform an infinite number of functions. They can consist of several small computational units that integrate combinations of lookup tables, registers, on-chip memories, and arithmetic hardware like digital signal processors. By combining these hardware components, FPGAs are able to execute algorithms with a lower latency and higher energy efficiency than similar devices like CPUs and GPUs. FPGAs offer flexibility to the design engineer, as changes can be made without making costly PC board changes. And therefore, you don't really need to create custom boards to implement a specific program application, as the FPGAs are reconfigurable. What's great about developing on FPGAs is that you can code your application to essentially be executed with as many work items as necessary. And for reference, each work item functions similar to what a core does on a CPU, which is essentially it's a single computational unit. The difficulty that comes with programming FPGAs is the long compilation times. Compiling a program can take many hours on the FPGA because the desired optimized custom circuit needs to be mapped out for the FPGA hardware it's to be deployed on. And this optimization problem is very complex. So to speed everything up, Intel, the company that developed the board we used, provides an emulator for the development process to ensure compilation correctness, and that the program runtime executes as planned. So the network was deployed on the FPGA using OpenCL, which is an open source C-based interface for parallel computing on various devices using task and database parallelism. OpenCL is an industry standard language to write hardware description language, or HDL code. At a high level, making programming FPGAs easier to do. It is supported across various hardware acceleration platforms as well, including CPUs, GPUs, DSPs, digital signal processors, and FPGAs. Therefore, we chose to use OpenCL as its non-proprietary language that provides a flexible implementation across many types of hardware accelerators, and greatly improves its impact and potential to be included in broader collaborations. The infrastructure used on this project focuses on CPU plus FPGA coprocessors, where the host program runs on the CPU and all computation is accelerated using kernels deployed on the FPGA. So OpenCL runs kernels, which are methods that are optimized for efficiency during compilation on the accelerator device. The kernel performs accelerated operations by taking advantage of the device's hardware architecture to parallelize task and database operations. The kernels are invoked by a host program, which is usually run on a CPU coprocessor. And the host program is responsible for managing the application as a whole. So there are many ways to optimize the interaction network implementation on the CPU plus FPGA coprocessors. Because this project is very much exploratory into how effectively FPGAs can be used for accelerating networks that do particle track reconstruction. There was a large motivation for the implementation to be adaptable to changes in network architecture. The design process on optimizing the program focused on finding the best kernel type to use, improving matrix multiplication operations, investigating device resource usage, lowering the bit precision of the data, and taking advantage of inherent efficiencies in the OpenCL language and FPGA hardware architecture. One such efficiency is double buffering, which really quickly, it allows for data for the next kernel that you want to execute to be transferred while a preceding kernel is already being executed. So it basically can improve your runtimes by just parallelizing tasks. The kernels we deployed are called ND range kernels, which rely on partitioning the data across work items on the device. So ND range means that each operation in an iterative loop is executed on an individual work item in a specific work group. The upside is that you can parallelize loops across each work item so they run concurrently, but the downside is that there is significant overhead when initializing the kernels to the data. This is especially true when dealing with dynamic graph sizes, which is inherent to the TrackML data. Each event graph has a different number of nodes, which represents hits, and also a different number of segments, which represent probabilities that the hits belong to the same particle. Therefore, you really need to consistently move data between the host and the FPGA, which is pretty much a co-processing approach. Apart from ND range kernels, OpenCL also allows for single work item kernels. This kernel type inherently parallelizes tasks instead of the ND range kernel, which parallelizes data. So you can generate custom pipelines, make loop optimizations, and control access patterns through directives called pragmas. Then each work item kernel task would run concurrently to others as necessary. So the image shown just demonstrates such an execution where the loop is executed by pipelining the tasks. This means that at each clock cycle, the tasks are initialized and executed in a separate work item concurrently to those already running. To select whether to use ND range or single work item kernels, I did a performance comparison between naive versions of single work item kernels and ND range kernels. And I'll show results on that later. But it's worth noting right now that I steered into ND range kernels initially because single work item kernels ended up with larger resource usage and therefore was a little less efficient in terms of data processing. So matrix multiplication is one of the largest bottlenecks in a neural network that includes linear layers. And this is actually where I spent a majority of my time. So optimizing matrix multiplication is a large field that I only briefly dove into. I mean, there are companies like PyTorch, Facebook, I mean, Intel, who spend years on this. However, there are many ways to take advantage of the FPGA architecture to parallelize matrix multiplication optimally. When doing matrix multiplication, there ends up being a significant amount of redundant reading from globally shared memory. Because it takes longer to read from globally shared memory than local memory or local registers, it's not generally good to have a ton of redundancy. So the way to reduce this redundancy is to split your multiplication into smaller tiles or blocks and read those tiles into on-chip memory. So qualitatively, this produced, just using local memory, ND range kernels produced similar runtime execution performances to Intel's in-house FPGA acceleration library. But then I want to step further with register blocking, which basically subtiles the local memory and stores values into registers so that you can do more work per thread or per work item, thus further reducing reading from global and local memory and using more of the local resources to speed up execution. So therefore, adding register tiling onto local memory tiling theoretically means that matrix multiplication should be even faster. So I compared the single work item kernel with just a naive implementation of that, initially with a naive implementation of ND range without any tiling and all of that. And then I also did it later with different iterations of matrix multiplication implementations in the ND range kernel. Overall, the ND range kernel led to better runtimes and used significantly fewer resources. This is the main motivation for doing everything that follows with an ND range kernel. Also in the end, adding register tiling does lead to even better runtimes of the overall interaction network. What's better is that it uses fewer resources in most architecture components than other matrix multiplication versions of the ND range kernel. So I did two different studies to test deploying the interaction network on an FPGA. I did a scalability study to investigate how the network scales with input data size, and then I also investigated how changing the bit precision of the data impacts resource usage. The data scales logarithmically according to PT cut. And the FPGAs were able to run data as low as a 1 GeV PT cut. That was the upper limit on data size, as that was when computational resources such as CPU, RAM, and globally shared memory started to exhaust. However, a 1 GeV PT cut corresponds to about 5,000 nodes per graph and a bit under 20,000 segments per graph. As expected, an increase in input data size led to an increase in execution times. The largest bottlenecks that factor heavily into scaling execution times are matrix multiplication optimization and the overhead time that comes with enqueuing ND range kernels. To save time, I won't really talk about these bottlenecks all that much, but I'll just note that I did spend a lot of time investigating these bottlenecks and proposing future changes and ways to really dive in and figure out what's going on. But what's notable about this study is that the co-processing approach shows that data of significant sizes can be handled quite efficiently. Of course, more optimization needs to be done, but this is a good first step into exploring the efficacy of the FPGAs to accelerate the interaction network. The bit precision study compares the performance of the interaction network on data converted into 8, 16, and 32 bits. The study shows that overall, the execution times are as expected, in that operating on 8-bit data takes the least amount of time, then 16 bits, and finally 32 bits takes the longest. At large PT cuts, the bit precision doesn't show a significant difference, but as the PT cut decreases, the difference gets larger. It still doesn't result in an incredibly large difference, but it's notable nonetheless. The more interesting metric is how the bit precision impacts component resource usage. In most components, a lower bit precision typically leads to a lower resource usage. So although the system area is dependent on more than just the bit precision, this shows that there are ways to implement the same algorithms at a lighter systematic load. So OpenCL, because it's C-based, it creates a custom data class or data type for 16 bits. So 32 bits represents something like a float, just a normal float. 8 bits represents something like a char or a character or something like that. But 16 bits is OpenCL basically created some sort of a custom data class where they do something a little different than just computing with normal floats, which is probably why the lookup tables are so large, or the resource usage of the lookup tables are so large. And then one last thing I'd like to note here is that the data of a PT cut of 1 GeV at 32 bits was too large for globally shared memory, but at 16 bits it ran fine. So the bit precision does impact runtime data utilization sizes too. So that's everything I have to present. And I would like to say a special thanks to Gage, Savannah, Bay, certainly Isabel, and everyone else who really helped out with my work. And I guess that's it. And if there are any questions, I'd be happy to answer them.
Thank you, Aneesh. Does anyone have any comments or questions for Aneesh?
Sorry, I just wanted to say that this was some pretty impressive work, and thanks for all the time that you spent on it.
Thank you.
Okay, again, thank you, Aneesh. Next up is Xiongfeng.
So, hi, my name is Xiongfeng Song, and I'm a master's student at Rice University. And my major is computational science and engineering. So this summer I joined the SkyhookDM team and help with server-side development. So today I'm going to present my works: the SkyhookDM projection-only pushdown and arrow dataset API integration into Skyhook objects. This project is mentored by Jeff and Noah and Ivo. So, so the Skyhook data management system, it features programmable storage for databases. It utilizes and extends object storage and classes in self-distributed system. It supports common data management operations like select, project, and aggregate, and so on. And these operations are pushed down, or it's called offloaded directly into the storage level. So now currently the two data format, the flat buffer and the column-based arrow data type are supported by Skyhook. And the overview is shown here. So we had 3 phases in my project. So the first phase, let me get familiar with C++ implementation of Skyhook's server-side code. And starting from some adding new features, I understood the basic workflow of data operations in Skyhook. Sorry, I added an execution flag. It's called pushdown columns only to the run query. So it pushes down only the projection and leaves the filtering operations to the higher level. And the second phase, in the second phase, the nested data type is considered, and we try to implement operations for the list array data type in Skyhook. And the last, we turned to the arrow dataset API and decided to integrate the new API with the SkyhookDM. So in the phase 1, we implemented a new feature to only offload columns projection to storage level, and we leave the filter operations to higher level. And why do we want to do such thing? Because the arrow data format is a column-oriented rather than row-oriented. So for example, when we want to do a query like select column A and B, well, A is less than 2 and C greater than 1. So such simple query operations. So here we only want to get the result of column A and B, but we actually need column C for the filtering. So actually we will need to use 3 columns, A, E, and C. So the physical layout of column oriented, here you can see the difference between column oriented and the row oriented. And so the features I added is trying to, in the storage level, we first select the columns we want to use and return it to the higher level to do the further processing. So that's the basic idea. And this is the flowchart I made to describe the modification to the Skyhook, to Skyhook server side. So on the left side, it describes original workflow to execute a query. So when the user input a query and this projection is to select the column mu1 and the predicate is A equals to true and B equals to true. A and B are both columns. So there's a query schema and the query predicate for the execution, and you will return the when you process the query and you return the result to a higher level, and there's a more processing step, but it will not be used for the left side. And what we want to implement, and what we implemented is to modify the query schema and the query predicate to the. So it's to set the query schema to all of the column, and the query predicate will be set as empty. And so basically, I was modifying these variables to change its execution order and to implement these features. So in the higher level, or it's called it's the client side, the real predicate will be down here in the query small processing step. And my major commit is shown here. So except for the pushdown columns only, this new feature, I also do such things like reconstruct the schema and press in more processing and fix printing data. And another feature I added is to append the columns directly when there's no predicate and when the row number is empty. And I also do the refactoring to the code, like extracting the indexing lookup from the execute query operation. So the first phase is mainly the software development to the Skyhook, to the SkyhookDM server side. And you can see my pull request in this link. And for the second phase is the list array and the reducers operations. As we know, a common data format in the HEP data is jagged array, or called echoed array. So it's a special nested data type, and in Skyhook, this data are stored as an arrow list type. So every column in the arrow table for the nested data type are stored as a list array, and we would like to implement some reducer operations for the list, so such as the min and max and count. And actually, I was trying to implement this myself, and I even designed some new operations. But Jeff said maybe it is better for us to use the common definition of the reducers rather than to design some new operations. And then we found some compute API in the arrow library we use. So there's a compute package in the arrow, and it has three types of APIs. One is scalar and aggregate and vector. So what we want to use here, and what is very helpful for our implementation here, is the aggregation functions. It provides some common aggregation util functions for the arrow list array, and we can just simply call it and to get the result. So I look into its documentation and the source code, and I write some, and I made some documentation for that. So, and there's some, and also when I was doing the phase 2, and the Apache Arrow has a latest release for its dataset APIs, so the compute API only provides some util function, and while the dataset API can do much more, such as projection and filtering in only one method call. After some discussion in Skyhook development meeting, we decided to move to the Arrow's new API and try to integrate them with Skyhook. Yeah, and about the dataset API, so it's C++ version. There's no documentation for that. So it's a latest release, and they have only some usage doc for the Python code, but there's no documentation for the C++ code. So I have to look into. So I have to dive deeper to look his source code implementation. So I spend much time here, and there's a flow chart. There's a workflow chart for the in our team meeting. So there's a result of the Skyhook new architecture, and what I was responsible for was the test setup for the storage side development. So so basically my work's done for the phase 2 are the two things. The first is to set up the Arrow CIS for the running unit test. I included and linked the libraries for the Arrow dataset API and also the compute API. And so I set up the running test environment, and also I set up the environment for the dataset API and that integrate our Skyhook. And the second issue is to create a in-memory fragment interface. I use the in-memory fragment in the dataset API to the object stores API. And there's a flowchart of the in-memory fragment I created. So I created it's a skeleton for the dataset usage. First, I create the error table, and I use the table batch reader and the schema from the error table to generate a in-memory fragment or in-memory dataset. So this in-memory fragment or dataset is very helpful, and is very useful for us because later we can create a scanner and there's a filter and the projection operations. Yeah, we create a scanner builder. It's a factoring class to build a scanner class, and inside the scanner builder we can call the filter and the projection, and this is what we want to use for the Skyhook development. Because with the help of these functions on this method, we can directly, so we won't need to write our own implementation for such things. And its error native method is quite safe and faster to use. So at last we can get the scanner and read the filter and filter data, and we can convert it back to the table and to get our data. So this is basic flow for the new data operations. And for the in-memory fragment, so this the scanner is material scanner operation. So these are the documentation inside the source code, and actually the filter method here is very important for us, as I said. So we can simply create an expression for our filter operation, and we can pass it the expression here, and we can get our result. So this will be much more convenient than the previous one, since we don't need to implement our own code. Okay, so thank you. That's my presentation. Thank you for listening.
Thanks, Xiongfeng.
Any questions for Xiongfeng?
I just wanted to say nice, interesting work.
Yeah, thank you.
Yes, agreed. It's very nice to see this moving forward, and I personally am really looking forward to when we make the integration with Service X to take advantage of some of this.
Okay,
Great.
thank you, Xiongfeng, and thank you to mentors and the fellows for your great work this summer.